Hello everyone, welcome to this video. In this video I will explain another substitution technique called as Hill Cipher. Okay, so this is a substitution technique where actually we are going to replace the m alphabets of the plain text by equivalent m alphabets in the cipher text. So this method is actually developed or proposed by a mathematician called as Lester Hill in 1929. Okay, so in this particular method, what exactly we are supposed to do initially is, before you proceed with the encryption algorithm, we have to replace all the alphabets in the plain text by equivalent numerical values, like say a equal to 0, b is replaced by 1, c is replaced by say 2, and like that, z equal to 25. Okay, so we have to make a group of m number of bits in the plain text, where m can be 2, 3, 4, whatever it is. Okay, so for the case m equal to 3, I will explain how the encryption can be done in this case. See, it is simple matrix multiplication. Okay, so we just have to multiply the plain text with a key matrix. Just look at here, what we have is, we have a plain text P, P1, P2, P3, because I have taken m equal to 3 here, and we have to consider one key matrix of the order 3 cross 3. For m equal to 3, it should be 3 cross 3. If I consider m equal to 2, in that case, we have to consider one key matrix, that is 2 cross 2. Okay, finally we have to take a mod 26, because whatever the cipher text you are going to get, I said we are going to replace m number of plain text by equivalent m number of cipher text. So P1, P2, P3 are replaced by C1, C2, C3, which should be an alphabet. Somehow we have to replace that by again the numbers, whatever you get through this mathematical multiplication process, okay, into the equivalent alphabet. So that's why we have to take a mod 26 over here. Okay, now how the multiplication is done in mathematics, matrix multiplication, it is very simple, right? Just look at this. C1 can be obtained by simply, just one second, let me erase the things which are not required here, just one second, yeah. So the C1 is obtained by simply multiplying what? This particular row vector by the first column vector, right? What about C2 then? C2 is obtained by multiplying again the same plain text, numerically represented plain text, by the second column. The third one is C3, can be represented by same row vector multiplied by this. This is simple matrix multiplication. In mathematics you have studied this. Okay, so this matrix multiplication can be represented like this also, that is C is equal to P into K mod 26, where this C and P are nothing but they are the vectors, okay, cipher text vector and the plain text vector, and K is corresponding matrix, key matrix, whatever we consider, taken mod 26. Okay, so that's what I mentioned here, where C and P are the row vectors with a length of 3, okay, and K is a matrix with a size of 3 cross 3, okay, which actually represents the encryption key. So encryption key can be anything. Now let us understand this method Hill Cipher by using one example. So this is the reference table I have taken over here, okay, so that I can match or map the alphabets with the number, and later the number to the alphabet after obtaining the cipher text values. Now my example is pay more money. This is the plain text I have considered. Fine. The key what I have considered is randomly it is taken RRF VSV CCT is the the key I have considered. Okay, 9 keys, so that I can represent that in the form of a matrix of 3 cross 3. 3 cross 3 is 9. Okay, so what we are supposed to do here is we have to convert these alphabets into the equivalent values and represent in the form of a key matrix. Okay, 3 cross 3. So this is what the matrix actually comes out to be here, because R means 17 here, correct? Just look at this, 17. So this actually forms RRF, actually forms the first row. Okay, F is 5. VSV, okay, V means it is 21. You can see over here, it is 21. So 21, 18, 21 is the second row of the matrix. CCT actually represents my third row of the matrix, that is 2, 2, and T is 19. So I know what is my numerical values for the encryption key. I have represented in the form of a 3 cross 3 matrix here. Next, I have considered, see, because m equal to 3 in this case, I have to encrypt at a time only 3 alphabets in my plain text. Then finally followed by MOR, then followed by EMO, and followed by ENIMA. Okay, so my first 3 letters are PAY. So the equivalent numerical values are like 15, A means 0 and the third letter is Y. So Y is 24. So I have considered this. Then what we have to do, C equal to P into K, right? That is the method. Nah? So I considered P, okay, into K, then mod 26. Okay, I perform this mathematical operation. So 15, 0, 24. I substitute for matrix K, take a mod 26. You know how to multiply this? These are the C1, C2, C1, C2 and C3. There's a small mistake over there. C1, C2 and C3. Okay, so I will get values like 303 after multiplication, again 303 and 531. So we have to take a mod 26, right? So after taking mod 26, what I'll get is, see this, okay? So 303, 303 and 531, mod 26 is nothing but 17, 17 and 11. And equivalent alphabet, ciphertext alphabet is 17 means R, okay? Then again 17 I have, so it is replaced by again R. And 11 is actually nothing but L here, right? So RRL is the first three ciphertext I will get for PAY, the plain text. Now I will consider MOR, okay, the three more consecutive alphabets. I will get the values like this. This is a simple matrix multiplication. You will get these values. That is 532, 490, 677. After this, process of multiplication, similar fashion, whatever I have done over here, okay, I'll get this. 12, 22 and 1 equivalent alphabets are M, W and B. Okay, so next you consider EMO and NEY. Okay, and finally we will get the ciphertext as RRL, MWB, KAS and PDH. So this is simple matrix multiplication which actually taken a mod 26 actually gives you the ciphertext according to the Hill Cipher method. Okay, now what about decryption? It is just the opposite of encryption. So we have considered a matrix over here, okay, key matrix, okay. So the same ciphertext whatever you have obtained, okay, should be multiplied by the inverse matrix of this, remember. So we have to find out, or we have to calculate the inverse of this. So C into K inverse mod 26, which is nothing but, okay, C is nothing but what? P into K, right? P into K. So it is C is replaced by P into K, multiplied by K inverse will give you what? P, because K into K inverse is always a inverse matrix, identity matrix. K into K inverse is nothing but it is the identity matrix. So P into 1 is P. So that means my algorithm says if there is a inverse for the key matrix, whatever we have selected, we can recover back or we can get back the plain text. Okay. Now, how to find the inverse? Again, just for your knowledge, I have mentioned here. Otherwise, in mathematics, you have already studied and know how to get the inverse of a 2 cross 2, maybe 3 cross 3, whatever the matrix is, right? Just for your information, just to get this, these are the steps we have to follow. Check the determinant of the matrix. So I have this example matrix. Say I found the determinant over there. Transpose the original matrix next. Okay. Then you find the determinant of each of the 2 cross 2 minor matrix. Okay, fine. So for this first case, that is taken as 1640. Okay, so 1640 we get minus 24. Fine. Similarly, you find for the remaining other minor matrix. Then create the cofactors. That's what we done. We need to find the adjacent or adjacent matrix. Then we have found out here. Okay. Then finally, okay, M inverse can be found by using the formula. This one. M inverse is nothing but 1 divided by determinant of M and the adjacent matrix of M. Okay. So this gives you the inverse of M. This is a 3 cross 3 I have taken. In the next slide, okay, so here I will take a 2 cross 2 matrix. So this is the example I have taken. Okay, 4726 inverse. Okay, this is nothing but the determinant. Okay, this is the adjacent matrix. Okay, so 1 by 10 multiplied by this will give you this. This is the inverse of a 2 cross 2. So for 2 cross 2 it is very easy. I have taken one more example from the textbook. Okay, my A matrix is this. Fine. Next, let me find the determinant of this. So determinant what I'll get is minus number. So there is no meaning for negative numbers in the Hill Cipher, remember, because my number should be always between 0 to 25. So I have to go for a mod 26. Okay. So whatever, in this case, I got a determinant as negative number here, minus 121 mod 26. Okay. I have to convert this into the positive number. How do you do that? Simply, you divide this minus 121 by 26. Okay. So minus 1, 2, and 1 by 26. Fine. So what we get 26 minus, okay. So it is how many times it goes? 26 5 times, I believe is correct. So 5 minus 5 is the quotient, okay. So I'll get 130 here, okay. So 130. So when I subtract it, what I'll get 9. The remainder as 9. So mod of minus 121 is nothing but it is 9. The same thing is done here. So we have to convert into the positive number, remember. Okay, whatever it is, determinant, you find determinant or whatever, you have negative numbers over here. Whenever you have a negative numbers, you convert that into positive numbers by taking the mod 26. Okay, so we know the determinant. Okay, 1 by 9 is nothing but 9 inverse, right? So we can find out even that inverse of 9. Okay, so inverse of 9, how do you find it? Okay, this is the method. 9 inverse mod 26 is given as 3. How you got it? Because when you multiply the inverse C, because C 9 into 3 is 27, okay, 27 mod 26 is 21, sorry, 27 mod 26 is 1. So the number, okay, when you multiply here the 9 with a particular number and the remainder what you get here, the modulus, it should be 1, okay. So for 9 into 1, if I consider this as 1, 9 into 1 is 9 mod 26, it is 9 only. Now if I consider this as 2 here, 9 into 2 is 18, 18 mod 26 is 8, right. 9 into 23 is 27 mod 26 is 1. So for this particular number 3, I got the modulus remainder as 1. So the inverse of 9 is 3. So you need to find the inverse of 3, okay. Then you have to multiply. This is the method I told earlier, right? This is the one way of calculation. But I said that we need a positive numbers over there. Okay, so in this case 6 is divided by 10, minus 7 is divided by 10, like that. But in this case, inverse is taken. 1 by 9 is nothing but 9 inverse. It is 3. It is multiplied by this. Okay, so this is nothing but adjugate or adjacent matrix, which we have shown here. Okay, then the minus 8, minus 17. Okay, because there is no meaning for negative numbers. So minus 8, minus 17 has to be converted into positive numbers. How do you do that? Same method. Okay, minus 8 divided by 26. Or else what you can do over here is, if the number are small, just add 26 minus 8 is 18. 26 minus 17 is 9. Okay, just subtract this negative number. Okay, should be subtracted from 26, will give you a positive equivalent positive number, or it is a nothing but it is a remainder or the modulus. Okay, so we got 3, 18, 9, 5 as the adjugate or adjacent matrix, because this matrix is converted into positive matrix over here, positive numbers. Okay, 3 into this will give you this. Okay, again I have a 54 over here, which is not allowed. We have to take a mod of 26, right? So this is the A inverse. Then we have A inverse here. Then take a mod 26. What we get for 9? It is 9 only. 54. Okay, mod 26 is 2. 27 mod 26 is 1. 15 mod 26 is nothing but it is 50. So we know the inverse now. Okay, you know inverse, and you can decrypt it by simply multiplying the inverse matrix with the ciphertext, taking mod 26. This is the method, right? So as I told, decryption need actually the inverse of the matrix. So in my case here, my key matrix is this. My key matrix is this. Okay, I find the determinant of this. I'll get it as 17. Okay, then I need to find the adjugate of the matrix. You know how to find the adjugate also. I have told, explained already over there. This is the method, correct? The same method we have applied earlier in the example. Okay, multiplying the the inverse determinant of 17, okay, with this adjugate matrix will give you the inverse. So this is the inverse matrix over here. Okay, so I have a K matrix. Just for confirmation purpose, I have a K matrix. I know the K inverse also. K into K inverse should be identity matrix, right? Just look at this. Take a mod 26 again. Everywhere we have to take a mod 26. So we get a identity matrix over here. So that means my calculations are proper. Okay. Now, so to summarize this, okay, we can encrypt the message by simply multiplying the plain text with K mod 26. We can get the decryption by simply multiplying the ciphertext with the inverse of K mod 26. Okay, which gives you again same P, the plain text. Now, for understanding purpose, I will take one more example. So I have taken one example over here which I have not solved. Okay, plain text messages short example using the keyword Hill. I have not given the matrix, but some keywords are used similar to playfair. Okay, so 2 cross 2 matrix I need. Based on the keyword, you can decide how many what should be the size of the matrix is. Okay, if they mention only 4 letters, it should be 2 cross 2, because I can translate this Hill into the numerical values by using this method by mapping only. So H means 7, okay, I means 8, L and L is nothing but 11. So I got a 2 cross 2 matrix. So I have to consider only 2 alphabets at a time here in this case. My M equal to 2. Okay, in this way you can whatever the keyword given, you can translate that into the matrix. Okay, but I will solve this problem. Okay, my plain text is Hill Cipher and the key is given as 3285. So they have given a key matrix directly as 2 cross 2. If they give a keyword, convert into the key matrix, then you perform the same operation like P into K mod 26 will give you the ciphertext. Now in this case we have to convert this Hill Cipher, a block, the plain text, whatever we have, into group of 2, right? So we have this group of 2 here, HI, LL, CI, PH and ER. Assign the equivalent numbers by referring the table over there: 7, 8, 11, 11, 2, 8, 15, 7, 4, 17. Multiply, consider only 2 alphabets at a time, that is, first one is 7 and 8, right? I considered it here. P into K mod 26, this is what we have to do. So C1, you know how to get it, okay? So this is C1, I got H here. C2, okay, that is multiplication, matrix multiplication again, 7 multiplied by 8 and 8 multiplied by 11, that's it. What we have done here. Sorry, my key matrix is this, I'm very sorry. 7 multiplied by 2 and 8 multiplied by 5, right? I get a 54, take mod 26, I'll get answer as 2, replace that by alphabet. So HI are replaced by HB. Okay, my second number is 11 and 11, so I take 11 over here, again multiply. Okay, so what is this? 11 multiplied by 3 plus 11 multiplied by 8, which gives me C1. Take a modulus, 17 R, okay, is the answer. What about C2? 11 multiplied by 2, 11 multiplied by 5, take a sum of both, I get 77, mod 26 is 25, replace that by a Z, refer the table. Similarly for case 3, okay, that is 2 and 8, case, this is the answer I have got, just look at the answers, matrix multiplication, that's it. Next it is PH replaced by 15 and 7, I got the answers like this. ER are replaced by 4 and 7, I got the answer like this. Okay, so now my ciphertext actually becomes, my Hill Cipher is replaced by some random text, not random, we got it from the Hill Cipher algorithm. SB, RZ, SS, XN, SP. Okay, now how to convert back into the plain text, I will see that in the next slide. Yeah, now again, so we need to find the inverse of the key matrix. Okay, my inverse is this, -5, 2, 8 and -3. By same method, whatever I explained in the previous slides, I have got it. No meaning for negative numbers, add 26 to it. Okay, that is 26 minus 5 is what? I'll get 21, 2, 8 as it is, 3, that is 26 minus 3 is 23. So I got translated into positive numbers over there. I got this as the K inverse matrix. Then ciphertext multiplied by this, right? My ciphertext is this. Divide into group of 2 numbers, okay? So 7, 2, 17, 25, 18, 18, 23, 13, 18, 15. So equivalent numbers I have taken. Go for a first case, 7 and 2, okay? Then multiply that by a matrix here, this one, 21, 2, 8, 23, okay? So I get H, I got I, okay? These two are my first 2 alphabets in the cipher, plain text, right? Second case, 17 and 25, go with this again. L and L I got, my first word Hill is done. Now I go to third case, S and S are my alphabets over here, right? Equivalent numbers are 18 and 18. So then again plain text 1, plain text 2, I got CI. Then the fourth case XN in my ciphertext over here, equivalent numbers are 23 and 13. Multiply, that's it. Last case, say this here, isn't it? Finally, okay, my cipher plain text is HILL CIPHER, which is nothing but my original plain text Hill Cipher. Okay, so the strength of this particular method is it hides actually single letter frequencies, the frequency of repetition or occurrence of single letters like A, E, T, most common letters, right? So if I use more bigger matrix, larger matrix, so it can hide more of the information. Okay, say 5 cross 5, 6 cross 6. A 3 cross 3 Hill cipher hides not only single letter but also two letter frequency informations. We have encrypted 2 letters at a time. Okay, so it is strong against ciphertext only attack, but you can very easily break this particular method by using known plain text attack technique. Okay, so this Hill cipher is also broken and cancelled. Okay, so in this method I have explained one more substitution method called as Hill cipher method. Hope you understood this. Thank you.